This is Anthony Abunaway with Microsoft, and today we're going to be talking about the ozone layer and addressing climate change in relation to the focus on the ozone layer. Now, back in 1980, scientists warned that humanity was on track to completely destroy the ozone layer by 2050. Without this ecosystem being a major focus, we would collapse. Skin cancer rates would skyrocket and life as we knew it would cease to exist. But today, the ozone layer is healing thanks to the focus on studying the ozone layer. In an unpredicted act, the world came together to prevent an environmental catastrophe. So how did we do it? And what can we learn from it? We'll be addressing that today. Now, the ozone layer or the ozone shield, you can even consider it as a belt around the Earth because it's a region of Earth's stratosphere that absorbs most of the sun's ultraviolet radiation. It contains a high concentration of ozone in relation to other parts of the atmosphere. Although still small in relation to other gases in the stratosphere, the ozone layer contains less than 10 parts per million of ozone, while the average ozone concentration in Earth's atmosphere is actually about 0.3 parts per million. The ozone layer is found in the lower portion of the stratosphere, from about 15 to 35 kilometers, pretty much 9 to 22 miles above Earth. Now, although its thickness varies seasonally and also geographically, the ozone is a substance that touches on our modern society in many ways. Like the ozone is used in an industrial process pretty much to disinfect the Earth. It's a disinfectant because the ozone is a strong oxidizing agent that is present in the photochemical smog. Because with the ozone in the stratosphere screening the surface of the Earth from a biological damaging ultraviolet radiation, it protects our society of humanity. Now, the ozone itself is a greenhouse gas in the atmosphere, hence really increasing the ground level ozone contribution to global warming, like we mentioned earlier. But on the other hand, a warming climate favors the foundation in accumulation of ozone in the atmosphere, mainly through two chemical mechanisms. In certain parts of the world, a warm climate changes humidity and wind conditions, leading to decreases in the frequency of surface cyclones, which results more stagnant atmospheric conditions, decreasing the dispersion of NOx and VOS, and prolongs the time for the reaction to produce ozone. Now, the data we used was from Wickenfen Air Quality and is a timeline between up to close to 20 years, from October 16th of 1996 to July 11th of 2016. Why our data is important? This is because of the instability of ozone and its inclination to return to its original form, O2. Both organic and inorganic substances may be oxidized by ozone, but also microorganisms such as viruses, bacteria, and fungi. It also causes many other issues, so that why we use this data in our analysis is to forecast the ozone level of next observation. This is a real-time problem for all of Earth and humanity if the ozone layer can not change and continues to be damaged. Now, the methodology used in the study was ARMA, 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 signal plus noise models for short and long-term forecasting. We also determined where the ASE value is lesser or higher and which model is more useful for forecasting. For this purpose, we use our language tools to complete our analysis. The results we were looking for were either stationary or non-stationary, and the hypothesis we were looking at were either data is stationary or data is not stationary. Now, my interpretation was both variables followed the assumptions of stationary because the p-value of the ozone is less than from alpha value of 0.05, which means hypotheses do not reject the conclude that ozone follows stationary. Now we'll be addressing the autocorrelation and partial autocorrelation in this slide. And the partial autocorrelation, basically, instead of finding correlation of a present with lag-like autocorrelation functions, it finds correlations of the residuals, right? Which remains after removing the effects which are already explained by the earlier lags with the next lag value, hence partial and not complete, as we remove already found variations before we find the next correlation. This is the view of the ozone ACF and the ozone PACF, the autocorrelation and the partial autocorrelation. First, we take the 5 smallest values of the AIC for further analysis from the ARMA model and the P equals F and Q equaling 1, the P equals 4 and the Q equaling 1 has the smallest value of the AIC, meaning that the ARMA models, the 4 and the 1, can be used in our study for good results or forecasting. Now, on this slide, I'm showing the interpretation. The ARMA 4-1 has 55,059.58 as its value of AIC. AIC is a metric that helps you evaluate the strength of your model. Similarly, the phi coefficient value are as shown below, 1.554, negative 0.6631, 0.16505, and negative 0.0582. And theta value is negative 0.9135. The 0.011, 13.48, 10.31, and 0.855, along with negative 0.0007. So the values were obtained for ME, RMSE, MAE, MASE, and ACFI representatively. Now, the figure here shown is explaining the spectral density of the true autocorrelation in the realization. So you're seeing the factor table, which reduces the order of factor into its first and irreducible second order factor. It's the value of the root cause to the one mean that is stronger of the strong characteristic in the realization, which is the REMA 411. And we'll talk more about that as we go on in the slide, showing the coefficients. What we're seeing here is the second factor plot, which is a signal plus noise of the first factor plot, which is also showing the coefficient of the original polynomial. Now, this is also a signal plus noise, which has the value of the intercept of the ARMA model, which is the realization of the forecast. This is the short and term and the long-term points of the ARMA. And What we're seeing here again is the long-term versus the short-term of the ARMA, the ARMA, and the ARUMA of the single plus noise model in the ozone on one day for the short and long-term forecast. We also determined where the ASE value is lesser or higher in which model is more useful for the forecast. For this purpose, we use the R language tool to complete our analysis. The data range is from October 16th of 1996 to July 11th of 2016. And we used Ozone for our analysis to follow the stationary assumptions. First, we checked the 5 smallest values of the AIC for further analysis for the ARMA. The P value equals 4 and the Q equals 1 has the smallest value of AIC, means that the ARMA for 1 can be used in our study for good results or forecasting. The ARMA for 1 has 550, which is the 59.58 value of the AIC. And the AIC is a metric that helps you evaluate the strength of your model. Similarly, the coefficient value are 1.554, negative 0.6631, 0.1605, negative 0.0582, and theta value is negative 0.9135. We've seen these numbers earlier in the slides with the 0.011, the 13.48, 10.31, 0.955, negative 0.007 value were obtained for the ME, the RSME, the MAE, the MASE, and the ACF1 representatively. Conclusion. In this study, we used ARMA 4.1, ARMA 4.11, and ARUMA and signal plus noise model in the ozone one day for short and long-term forecasting. We also determined where the ASE value is lesser or higher and which model is more useful for forecasting. The ARMA 4.11 has 55,085.88 value of AIC. With the AIC is a metric that helps you evaluate the strength of your model. Similarly, the coefficient value are shown as below. Now, the confidence interval was also best for ARMA 4.11 model, which is less than from other models. The ARMA 4.11 model can be used for ozone prediction or forecasting if it provides us the best results than other models. And here are my references. And thank you for listening to the presentation today.